Hello fellow skeptics, I'm Luther Name, and this is the 11th video in a series of videos on the broad topic of, is something wrong with modern physics? And if so, what, and can it be fixed? Now in the last video I talked in some detail on the Doppler expression, where it came from and how we've used it, and some of the things that we've attributed, some of the things that we can attribute to the Doppler expression that we have heretofore attributed to some of the other, what I'll call them, funky physics associated with the classical description of special relativity. I showed that many of the things that we had attributed to this strange physics associated with special relativity is really an electromagnetic phenomenon, specifically the Doppler. But the Doppler and the aberration effects go together. The role that aberration plays with respect to the Doppler is similar to the role that the generalized Newtonian gravitational model played with respect to the inverse square model that we use and use effectively, and with it being a heuristic. Now the Doppler is not a heuristic, but in terms of the details of what's going on with respect to the Doppler expression and how it works and what it is enriched by the presence of the aberration effect. Now the problem is that Einstein typically didn't develop his scenarios and mathematical descriptions based on real measurement scenarios. But it turns out, ironically, that if you take a good look at the way he developed his Doppler and aberration expressions, there is a measurement model there, but he didn't know it. And if you don't look at it, his approach the correct way, well, then you really can't see that there's a measurement model there. But since that's my focus in terms of what can you measure, you can't see something if you can't measure it. What I want to do is to explain in a little bit more detail from a measurement point of view what's happening with the Doppler and aberration equations themselves. So what I'll do is first describe in a little bit more detail what Minkowski's reformulation is and why I believe it's incorrect. And then I'm going to look at the aberration, and I'm going to look at and describe another way of getting to these equations themselves, and to show physically what's actually going on or what's happening, and develop some other models that I'll go into more detail on in the next video, where I'll talk about the things that you can use the aberration to explain, or at least a way of explaining things that heretofore have had no explanation. They've remained anomalies. They've remained things that we've seen, we've measured, but we don't know where it came from or why the measurements were what they were. And you may be surprised at what some of those are. They're not well known outside of a fairly narrow group of technologists who've puzzled over this and have come up with some explanations that are just flat out wrong, or at least incomplete, in that they don't include some of the other physics that we've been discussing. I've made the point in prior videos and this one that Minkowski's reformulation of special relativity actually did a great disservice to the physics community. It's wrong on very many levels. In fact, there's so many inconsistencies that you wonder how over the last 100 years it's been justified. This is one of the great failings within physics, that they haven't really dug down into the antecedents of a great many of the equations and physics that they basically use. So what we have here, what I'm going to talk about here, is Minkowski's reformulation, and I'm not going to read it line by line, but what I'm going to do is kind of summarize it as I go through it, so that you get the gist of what the errors are. The big issue is that there was a heuristic that everybody used. Nobody knew where it came from, but they all used it. Einstein famously tried to derive it, couldn't. So it remained undiscovered even to this day, even though the clue exists as to where it came from, and nobody's bothered to follow those breadcrumbs. Uh, it was laid out as a three-dimensional uh, equation. In reality, all we deal with are rays, uh, plane waves, waves propagating in a single direction. So you don't need to have the three-dimensional form at this particular point. Though later I'll show you where you do in fact need to have at least a two-dimensional representation. And I'll explain that when I get there. So what we do have is a heuristic given first by this, and then this is the way it's actually used. And what Minkowski noted was that he could come up with this term by producing an imaginary component here. So instead of x, y, z, he had x, y, c, and then a ICT or a t component. So he made his famous four vector in the normal three dimensions, and then the fourth dimension being time. So, and he was able to do this because when you multiply an imaginary times itself, you get -1 as a factor. So that's what he did. And what happens is, though, when you take this, if you take a look at what we look at as the phase of a propagating electromagnetic wave, you can transform it to make it look as though it's the propagation of a kinematic wave. Or this should look familiar. Doesn't that look exactly like the form that Minkowski was using, or at least toying with? Since x equals ct, then x squared equals c squared t squared. Where else could it have come from? So what happens, though, is if you take that ICT as a component of the four vector and you put it back in the propagation, what happens is it collapses the propagation. It goes to zero very quickly in the passage of time. Doesn't support propagation. So that's the first anomaly that you have. The next anomaly is that if you take a look at this same equation and you'd say, well, it's a quadratic and you can factor a quadratic. And so you would think that based on the way we normally do it, you can get this type of components for the factoring. But in reality, if you go ahead and you multiply those together, you can't get that. This has no factors. You can't factor it. So that's the second thing that's an issue with respect to what he's doing. And if you take either one of those factors and you plug it back in the way we did before, again, the equation the propagation equation either goes to zero or it explodes, goes to infinity. Doesn't represent wave propagation. It just doesn't. So with that, what I'm going to do is I'm going to say it's a very bad attempt at reformulating what Einstein was trying to explain. As successful as it apparently was, these are what I consider to be the only real aspects of special relativity, which are the electromagnetic components, the Doppler and the aberration. Now, we haven't really talked about the aberration. That's a little difficult to get your arms wrapped around. It's a different concept. Einstein didn't clear things up because he says, well, the aberration is the result of speed alone. That's all, just speed. And that's not quite what's happening. So what I'm going to do is I'm going to get into a discussion of what the aberration is and where it came from. That way we have then a complete understanding of those two equations, the physics that's involved, and how these represent then what we really have as the true special relativity. So the first thing is to figure out where it came from. Okay, and what I'm going to do is I'll show you how Einstein viewed the scenario, the geometries that he was calculating, and you'll see it's kind of confusing. When he set up using the Lorentz transforms to find the Doppler and aberration expressions, this is the geometry he was using. Now, this is a generalization. Instead of propagation in the x direction, well, it's a kind of a general propagation, and you have got the radiation moving in at another angle we call phi. And so this becomes a two-dimensional in the sense that two vectors form a plane, define a plane. So instead of 3 dimensions being reduced to 1 dimension, we've got the 3 dimensions reduced down to 2 dimensions. And so he works with the angle phi and the components associated with that. But what he has is this. He has an undeviated radiation. What happens is that if you're moving at an angle phi relative to the direction of motion, if you're moving at an angle phi, phi, relative to the direction of propagation of the radiation, then you have a problem in that if you're actually measuring that, you're looking at the supplemental angle. You got to be looking at where the ray is coming from in order to be able to measure it. So even though he does his calculations based on this angle phi, this is, if you're doing an experiment to try and measure what's happening, this is the angle that you've got to put in. And they're related as supplemental angles to one another. Phi plus theta equals 180. Phi prime plus theta prime equals 180 degrees. So you can always model it, but it's an awkward geometry. So what we have though is that the radiation is deviated. The aberration is the difference between these two angles. It's phi prime minus phi. That's just the deviation angle, but the deviation itself is the difference between these two. So what you can do though is that original expansion that we showed, where you can basically reformulate the complex phase of the propagating wave from this into this, we can go further than that. You can change it into a flux, and I prefer to work with fluxes. Frankly, I don't believe that the wave formulation is really a description of what's actually happening. Maxwell's wave equation, Maxwell's equations, all of these equations are basically modeling what's happening after radiation is interacting within matter. And it has to do with currents. And so what we've got are models that we say represent propagation of electromagnetic radiation, and they're not. They're merely a description of the fact that we've detected that radiation, because you only know that radiation exists because you can detect some effect of it. In the case of the interaction with electrons, you've got currents. And so you've got stuff happening within bulk matter. And that's what you're modeling. And so that's what those models are. It's not a wave like a water wave or a sound wave. It's different. I prefer to look at it as a flux. And so I'll describe what that is in just a moment. But if you've got a photon with energy E, then it's given by h times the frequency. And so we know that photons or electromagnetic waves also have momentum associated with them. And that is given by an equation. This is where h is the Planck's constant, divided by these fundamental factors that we use to represent electromagnetic radiation. And we got a momentum that's then given by the energy divided by the speed of light. These are well understood. So what we do though is this. If I look at those equations again, and I put a Planck's constant in there, I can change the form of these. Now, while I multiply by the Planck's constant here, what happens is I don't have to worry about that. I put it into the equation. It looks like I'm just sticking something in, but it turns out that I can do it to both sides of an equation, right? I can put the same thing in on both sides of an equation. And so that's what I do down here. I put in Planck's constant, and what I find is that I can represent the complex phase as a function of both the momentum and the energy. So what we have here is, if we take a look at how the Doppler and aberration expressions were defined or found or calculated, uh, they really represent a conservation of energy and momentum, uh, where you have an observer moving at one speed, and then you have an observer moving at another speed. This P is actually a vector, and so what you have is an angle in there. The angle of P can then be relative to X. E is a scalar, P is a vector, and so you have here uh, a P dot X is a scalar and a scalar, and so what you have here is the equivalent to what Einstein used to find the Doppler and aberration, but we're looking at it in terms of energy and momenta and the conservation of it between the two frames that we're making the measurement. Now, what's a flux? A flux is a quantity of anything, water, gas, photons that flow through a unit area in a unit time. For photons, an energy flux per second is energy per unit time, which is power. We also have that if we've got an object that is being impacted on by a photon flux, energy per unit time, we know that there's a change in momentum of the photons as it hits that. It can be absorbed, so it's stopped, or it can be reflected off at some angle. We always, from a conservation of momentum perspective, we have then a way of having a change in momentum at the surface that's intercepting flux radiation, and change momentum is a force. And force per unit area is pressure. So we can relate an incident flux of photons per unit area to a pressure. And Einstein, in fact, had a radiation pressure model that almost nobody has remembered or given any credence to in that 1905 paper. And and in that, what he does is he shows how the Doppler expression, at least the Doppler, he did not consider the aberration, which meant that it was an incomplete model. So that means that we can find the Doppler and aberration expressions in terms of the conservation of momentum and energy. It's a measurement model. And Einstein never did measurement models, but now we can begin to understand what the aberration is, because we can relate the aberration to conservation of momentum from one frame relative to another frame of motion. So, and that irony, of course, is that Einstein never developed his measurement models, but he inadvertently did develop a measurement model when he was finding the Doppler and aberration equations. So what I've done is I've discussed in some detail what I feel is what special relativity is all about. It's the Doppler, and it's the aberration, and it's electromagnetic radiation. And what we've seen or called the various phenomena that we attribute to special relativity, the kinematic types of things, is really because our measurement process has been deceiving us in a sense. We use electromagnetic radiation to accelerate electrons or particles, and we've measured the interaction of these particles in matter. And so what we've done is we have convolved a series of events that have been occurring. We are limited in terms of how we can accelerate because of the way the Doppler effect impacts the forces on a charged particle, and we don't have any other good way of reaching what are called relativistic speeds other than through the acceleration of charged particles with electromagnetic waves. So that's what we've been measuring, and we've been looking at these various experiments. We haven't used all the physics or employed all the physics in understanding and discussing what these experiments are trying to tell us, and then we're misinterpreting it. So what I'm going to do here is that's all I'm going to talk about at this particular point. I alluded to the pressure associated with photon pressure, or pressure of an electromagnetic wave. That's important. I mean, in the prior discussions where I talked about how the Doppler effect impacts the acceleration of charged particles, well, the Doppler effect limits how fast they can go, but also the Doppler effect acting on ambient radiation, black body radiation, provides a counterforce. That again limits how fast you can go. So what I'm going to start to do is to talk about a variety of physics and technologies, things that we use, and I'm going to do it within the context of what the Doppler and aberration equations are telling us about the technologies and about the physics that we're working with. So that's going to be the topic of the next video, which will be number 12 in the series. So I'm Luther Name. Thank you for watching. Please leave a comment, and I'll be back with you shortly with the next video.